I'll just wait a bit to see everybody join in. Sorry for the late start there. For those who are just joining in now, since it was a late start, I'm just going to wait a couple extra minutes. Okay, I'm not seeing more people join. Hopefully we didn't turn everybody away with our few-minute delay there.
Oh dear.
Well, maybe to just get things moving, maybe people will join in later. I think we might as well just get started. Welcome everybody to the second day of ACI-Ontario's Fall Concrete Webinar Series. Today we have Graeme Stewart from ERA Architects. He's also founding director of the Center for Urban Growth and Renewal. And just to get things moving, I'll hand it right over to Graeme.
Okay, thanks so much for having me. So today I'm gonna really pleased to be part of this session. It looks like a great program that you guys have. I'm going to be talking about the Soble Tower, which is a passive house retrofit that is in mid-construction. It's slated for completion in early 2021. Project that's been on the go since 2017. And I'm going to give a bit of an overview of what this type of project is about. It's a major retrofit project with a lot of concrete restoration and really using the concrete frame of this original building as a key asset. And looking in terms of some of our analysis around when do you keep an asset, when do you replace one, and what does deep energy retrofit look like? Quite a lot of interest now in retrofits in terms of job creation and products and the potential for the built environment. So these are the buildings that we're looking at in several of our projects. It's the mid-century 1960s, 70s apartment slabs. And there's quite a bit of work that's gone into looking at ways of rehabilitating them and keeping them as key housing for the next generation. And the Soble project is a marquee project in looking at what does best in class look like right now with today's supply chains. When we look across the country, this housing is ubiquitous. It's everywhere. There's over 730,000 households living in housing like this. And the strategies that you would use in order to do retrofits here also can spill over into looking at other built forms, but also newer housing, that sort of aging condo housing and new construction in terms of achieving best in class. With this housing type, a lot of it is quite old. Some of it's over 50, 60 years old, and failures are beginning to happen. This was a building that had an electrical failure that required the building to be evacuated. and 1,000 people were actually effectively homeless and had to be housed elsewhere for over a year as construction happened. So one of the reasons that owners are interested in this and housing authorities are interested in retrofit is to avoid catastrophic failure that can happen. And so looking at the ecosystem, it's the financing, where does the capital come from to do this type of work, to what standard, and what are the criteria by which you engage in retrofits, and then the retrofit industry. What is the state of the supply chain, and what is the state of the trades in engaging in deep retrofit. A lot of this work has been ongoing in terms of groups and meetings and advocacy that actually helped establish a major kickoff to this cross country, which was the National Housing Strategy, which now has a goal of the retrofit of 200,000 of these types of units across the country, with financial support of up to $15 billion over 10 years. So there's quite a lot of capital now available to do this type of work, and the first generation of these projects is unfolding. So this is the Ken Soble Tower. So it's located in Hamilton. It's owned by City Housing Hamilton, and has some pretty ambitious targets. And I think what's great is that this was really led by the client, by the owner. City Housing is quite an interesting organization, and a new CEO who basically came from a healthcare background and said, in Canada, we have world-class hospitals. How come our housing is so substandard in public housing? So his goal is to revamp Hamilton's existing housing stock to 21st century standards, as well as introducing passive house as their standard for new construction. And this is what the building looked like when it was opened in 1967, and then here it is a few months ago under construction. The standard that the building is done by is called Passive House. Probably many of you have heard it, but it's a standard started in Germany, very low energy. And the main theory behind it is by isolating the envelope through effectively an airtight envelope with high R values and U values for windows, that you can dramatically reduce your heating and cooling loads. And in addition, for fresh air delivery, you need there to be heat exchangers, ERVs or HRVs, in terms of ventilation passing through the building. It started really as a standard for single family homes and is now scaling up. And the city of Vancouver, for instance, requires that all new public buildings be of the Passive House standard. What's interesting about this is a standard called Enerfit, which is their retrofit standard. So it's looking at applying Passive House principles to a retrofit. And this, the Ken Soble Tower, will be the largest, or is the largest Enerfit project presently in North America. So exciting, and a lot of learnings about how we might scale this. When we go into buildings like this, we work on older buildings all the time. Our practice focuses on adaptation and retrofit. They're really like these old cruise ships, and most of the services are well past end of life, and really the concrete frame is the robust piece that's sort of holding it all together, that gives this building life for another generation. The targets we looked at through meeting Enerfit is 94% reduction in greenhouse gases. We modeled it to look at to make sure the building was comfortable and resilient for 2050 climate data, in which Toronto is much warmer than it is today and much more humid. And the funding requirements from the federal government meant we had to convert 20% of the units to meet CSA barrier-free standards. So quite a lot of work to bring it up to barrier-free code, which we'll get into. This is some of the reworking of amenity spaces. It's a seniors building to make sure that it was able to provide good delivery of services as a seniors building. So some reworking of common spaces and outdoor spaces. These were the units in purple, which were converted for barrier-free. So had a lot of moving around of stacks and locations of kitchens and washrooms. And this is some of the visualizations of, what it looks like when all the hoarding's off. And what's quite important is that when we engaged in this project, yes, there's meeting the energy targets, but it's also balancing that with comfort and health and life safety. So one of the life safety measures was adding sprinklering throughout the building. The building was not sprinklered before. And it is quite possible and quite easy to make do a low energy retrofit in which you're actually making it actually less comfortable place to live. So this really balances, both through the Passive House standard and through the way the design team approached it, is how do we have a comfort first approach, and then a co-benefit is dramatic low energy. So this is a typical unit, kind of pulling off the envelope. It's a concrete frame building. The assembly on the envelope is block back up with a brick veneer. And this is sort of the list of liabilities, let's say, that the building had. So there was mold discovered throughout the drywall on the envelope, on the outer wall side, original windows, deteriorating slab edges on the balconies, anything that could go wrong with this building, you name it. And it was in such a period of, or a process of deterioration that the owner had emptied the building. So it was an empty building by the time we got involved and was not fit for habitation. This is the retrofit program. So full systems upgrade, new kitchens, new flooring, new washrooms, upgraded amenity, dealing with all the issues of state of repair. But specific to the Passive House program, robust new overcladding and new envelope to meet an effective R38, triple glazed windows for windows and doors, heat exchangers, and ERV ventilation up through the original bathroom exhaust. And we took a strategy of a centralized air distribution approach using the existing ductwork, but then did direct ducting through corridors into each suite. And this is what it looks like when you do the barrier free. So if you go back and forth, the location of the kitchen and washrooms actually flips, and that's to provide a large barrier free washroom and a new modernized kitchen. So quite a lot of work on those 20% of units, which in this case is roughly 38 units. Then working with our engineering team, which included TransSolar from Germany, as well as JNV locally, we did a lot of intensive modeling of what is the perception of comfort at different exposures at different time of year. And the main issue was preventing overheating. When we brought in such a robust envelope, the cooling or the heating loads go way down, and keeping people warm in the winters isn't the issue. It's really the issue of mitigating overheating in July and August. And so this is some of the results from the data, also including the 2050 climate data, where we were able to ensure that we could keep people comfortable within those ranges, but it required a process of providing an active cooling system to the building, which is unusual for Passive House. They try to have no cooling systems, but we felt it was required, especially because it's a seniors building. And so we had a 5-stage passive to active cooling strategy, starting with just by blackout blinds and robust envelope with a very small window to wall ratio. There's not a lot of heat gain. And then a ceiling fan, inoperable windows for air movement and shoulder seasons, but then a centralized dehumidification and active cooling system for when it's really needed. And this isn't the type of AC that gets you to like 20 degrees on a 35-degree day, but we get you more to 26 degrees and dehumidified as a central delivery. And this is interesting. This is some work we did with another set of consultants that really looked at sort of survivability and dealing with climate shocks. And so this is the inverse of a hot day. This is a cold day. And the way to read this chart is the bottom line here is outdoor temperature. So it's a cold February day where it's -20 in the evening. The blue line is what an OBC building, how an OBC building would perform. And the yellow line is our building. So what's interesting is that according to Toronto Public Health, if it goes below 10 degrees in indoor air temperature, then the owner of the building is required, if they can't keep the temperature above 10 degrees, to evacuate the building. So when power goes out, which happens during ice storms and other issues, people need to be removed from their buildings so they don't freeze and it doesn't get down to 0 degrees. When you look at our building, so in an OBC building, that would happen within 1 day. So within 1 day, you're down to below 10 degrees. With the Passive House level building, because of the robust envelope, you've got up to 5 days. So this is an example of some of the co-benefits that owners are quite interested in going with Passive House, and that their buildings are more resilient for these other types of issues. This is just looking at the building pre-construction. So, it's actually in pretty good shape. All the pole testing for the masonry and the walls was good. Good bonding. The concrete frame, by and large, was actually in very good shape outside of the balconies. And so this looks at how we achieved the envelope. So getting to an R38 is difficult, right? That's a lot of insulation. And for the most part, the idea is you do it through overcladding from the exterior, mainly because most of these buildings are occupied. You know, it's very rare to have an empty building. So our first design was a 2-ply system where along the backup wall and the masonry, you can here see the slab edge, we put on basically a thermally broken structure which contained mineral wool batt insulation, then a sheathing layer, and then on top of that we had a 6-inch mineral wool ephes layer. So quite a lot of components and quite a thick envelope. So that was the basis of design. But we didn't quite make it to tender to be able to test how did the market respond to this, because halfway through, well, almost at the tender date, pervasive mold was found throughout the exterior walls. And this was not included in the owner's hazmat report. And it actually is likely to have occurred as a result of the building having been unoccupied. So during the design process and after the original hazmat reports, this mold developed because the building was empty and not kept at high temperatures. So it posed a challenge. So we had quite a bit of remediation work to do on the interior. And so we developed a different strategy. We said, if we're going to be ripping out the interior anyway, let's put 6 inches on the inside and then reduce the complexity of our overcladding to a 6-inch mineral wool ephes. So this is the one we eventually went to, and that's what was the basis of design. Another piece of meeting passive house is a high degree of air tightness. So the minimum is 0.6 air changes per hour. And so a lot of the verification is doing quite a bit of air testing before, during construction, and post occupancy to make sure you've met that target. So a lot of the air barrier becomes one of the most important things. And a lot of passive house projects you may have seen use a lot of blue skin and tapes. And there's a real issue about no puncturing your barriers. Because of the particularities of this building, we decided to go with a cementitious and liquid applied air barrier that was painted on effectively the entire exterior envelope, which removed a lot of the finicky challenges with taping and folding of membranes. Another piece with passive house, which is interesting, is you have to do a whole series of modeling of every detail. Doing therm modeling to look for how the detail's performing, and these are then certified and validated by a third-party certifier. So this is an example where we're looking at a window detail, the positioning of the window, and the use of a typical steel angle versus a fiberglass angle. So a fiberglass angle, of course, has a bit of a cost premium, but here you see it performs much better. And effectively, what we have is an energy budget. So the energy budget for an Retrofit project is 25 kilowatt hours a square meter. When we started with this building, it was at 350. So we had to get from 350 down to 25. And really to get through the design process, through the big moves, you can get from 350 to 50 relatively easily. Not super easily, but you can, by doing the big moves, you can get there. But getting from 50 to 25 is the real challenge. And that's where you're looking at component by component, how you're able to chip away and to meet that budget. This is the windows going on. This is a few months ago. So big, beautiful triple glazed windows with a high degree of operability. We used silicone transition strips to be able to go from the window frame right to the air barrier on the outside, and you can see that liquid applied air barrier, and then with a silicone seal, and silicone can be applied in all weather conditions, was part of the reason we use this system. And then this is a more recent photo under construction with the ephes, the mineral wool ephes going on the exterior, which you can see here, and then tying into where the windows are. This is just a few months ago, actually. So actually, more like 1 month ago. So there's been, this is about the state that we're at. So you can see all the windows and the piece going up. I think the overcladding is mostly on by now. One issue that we were challenged with was dealing with balconies. So balconies are amazing thermal bridges. They're like radiators. And so to meet a low energy building, and especially a passive house building, we have to address them. So this was a study we did where we looked at 5 approaches of dealing with balconies, including leaving them exposed, like wrapping, like the original condition, wrapping the wall but leaving the balconies exposed, wrapping the balconies and enclosing the balconies. And what we found is typically when people do less stringent energy projects, they leave the balconies exposed. But what that allows for is a real mold risk, because you have a real thermal bridge now that's, instead of it being, the way it works now is you're basically heating outside and keeping the slab edge warm. Where you actually have a better performing wall that becomes a thermal bridge that brings a real cold spot to the interior by the floor, which is a real mold risk. Wrapping the balconies is it's a real finicky detail and quite a lot of work. And the other one that seems to be most popular in Europe and elsewhere where they do this is some form of winter garden or enclosure of the balconies. Working with the owner, because this was a seniors building and a barrier-free building, there was about a 6-inch gap between the door down to the balcony, and they felt that it wasn't accessible, or it wasn't possible to make it accessible, so they opted to remove the balconies. To keep the amenity of outdoor space, we've added a Juliet balcony, which is a door that fully opens with a guard. So you can see that here. So this is where the balconies have been removed, and then this is the floor to ceiling glazing plus the Juliet, and the inside looks like this. So you'll be able to open this up from the interior. They'll yet to be installed, but there'll be a guard here. So you'll be able to get fresh air and that outdoor access. But in terms of the design challenge of addressing balconies, in most cases, balconies will not be removed. The residents enjoy them, people are living in space. So the solutions to dealing with that thermal bridge is an ongoing and interesting design challenge. There are some companies based in Europe that have Canadian operations that do balcony enclosure systems that are worth taking a look at. The other one is the air tightness changings or the air tightness testing. So when we started this, the existing condition is about 5 air changes an hour, and we need to get to 0.6. But the guarded tests, which we've been doing throughout construction, which is where you do just a floor or just a room, or passing with flying colors. So we're very optimistic that meeting the 0.6 won't be an issue, and we're getting much less than that as we test through construction. And this is the building going up, and this is some of the interiors. If I actually go back to this slide, this is I'll go back to that balcony slide. You can see from the exterior, this enclosure at the bottom where you see the plywood and all of the plastic membranes, that's actually a unit that's being air tested. So you have to make sure that there's a perfect exterior seal, and then you do your tests. So it's a bit of a new domain. There's experts in this field, and it's one of the only real verifications you have to do in the field regarding passive house performance. The other ones are you just need to document through field review and through verification of the products installed or were those specified. So post-construction, we're quite excited. We're working with CMHC and the University of Toronto in a 3-year longitudinal post-occupancy study. We'll be looking at the performance of this building, but also some of the secondary benefits like health impacts, safety and security, housing quality, operational, et cetera, et cetera. It's really looking at what are the larger scale benefits of engaging in a more advanced retrofit. So happy to share those results as they come in. And part of those is in putting a series of robust sensors throughout the building to really test air quality and levels of comfort and temperature in all the different exposures. And then this gets back into this sort of pinwheel here, which is looking at finance standards and retrofit. And in this case, because it was an owner direction to meet Enerfit, that really drove the project in terms of how do we get industry to kind of meet the expectations of this rigorous standard. And I think as a first of its kind, there's already a whole lot of learnings that will help the next generation of these projects. On the other side of the mountains in BC, because of the BC STEP code, there's quite an advancement in both training and supply chain, which is fantastic. And so, for instance, the windows that we used in this project are fabricated in British Columbia. And there's such a push towards passive house in that market that fabricators are starting to open up shop and open up businesses to service that. And if we'd done this project a few years ago, those windows would not have been available in the Canadian marketplace and would have had to been imported from Germany and elsewhere. So things are beginning to move, which is exciting. And this is what gets into some of the other push and pull factors. So one is standards. This is looking at the City of Vancouver standards, which is really a top to bottom way to promote passive house, both through zoning relaxations and then base standards in terms of meeting the STEP code. In Toronto, we have the Transform TO, which is the climate plan, as well as the Toronto Green Standard. And it's not a fully understood or people don't fully grasp the sort of direction the Toronto Green Standard is going, in that it is a STEP code that on every other year or so, it goes into the next phase of what base compliance looks like. And by the middle of this decade, base compliance will effectively be passive house. So there's a lot of work we all need to do to ramp up to get ready for when these are the base codes. The trick is that all of the standards that we just mentioned in Vancouver and Toronto and elsewhere relate to new construction. So retrofit, there's still fuzzy guidelines on what is the base requirements of retrofit. And showing this sort of horrific slide, I was actually in London when the Grenfell tragedy happened, and was there, for related but other reasons, but was able to actually meet with City Hall and the fire marshal and people on the ground, and what was actually happening. And this is the utmost example of a failure of design compliance and failure by design professionals, but also of local authorities and code reviewers. And it was just sort of like a 360 failure that led to this disaster. And following that, we looked at the Canadian codes in regards to what is the guidance in the code to avoid something like this. And there's very little guidance in terms of existing buildings. I mean, you need to meet Part 11 and make sure, which is great. We have Part 11, but in terms of looking at mitigating mold risk through window changes, adding ventilation now, which is totally top of mind because of COVID, we don't have, there's not the guidance that there should be. Whereas in building codes like the German building code, it's very spelled out how you address existing buildings. This was the case a few years ago. Grenfell happened in 2016. Or 17, now just released last August is the alterations to existing building recommendations report from the Canadian Commission of Building and Fire Codes. And so there's a lot of movement now happening on the development of a national model code for existing buildings. And I think that the push factors of both climate resilience as well as COVID and ventilation. I know ASHRAE's developed a white paper and is really working towards ventilation requirements for COVID. That these we imagine will be front and center in all retrofit projects and certainly inform the way we approach our work. And so when we look at that, some of the codes and standards that make sense for a retrofit for health and COVID is just what is the fresh air delivery and air change rate? Often it's very inadequate in existing buildings. GHG reduction in terms of both embedded energy and low carbon performance. And climate resilience in terms of things like making sure that we're not using flammable insulation. There are ways in which flammable insulation is acceptable under the OBC if it's covered by a cementitious material or other things, but we've taken the tack to say we're just not going to use it in our projects. But in terms of supply chain and trade readiness, which is interesting, is that while Rockwool provides with Durock, they provide an EFIS, a mineral wool EFIS product. Not many trades have installed it. So the Soble Tower will be the largest application in the Canadian market of that product. And so there's interest both from those suppliers and others to say, hey, wait a second, we can actually market this as a overcladding product that's safe and low carbon. And then to advance this work, we've been working on a few things. One is really looking at some of those supply chain gaps and how do we advance the retrofit industry. And another one is working with CMHC on a field guide about how do you engage in retrofits with residents in place, which is a whole different thing than doing an empty building. So in terms of accelerating the retrofit industry, what you're looking at here is some retrofits from the UK, where in terms of snap in place ductwork and snap in place protection for sprinklers and this ERV system that you just put above your toilet. These are low cost and high impact products that are just not available in our market yet. So there's some work to do there. And then this is, I'm not going to obviously read this off, but this is sort of a green, yellow, red indication of retrofit products that are available or not available in our market, and quite a lot of them that would be fantastic to really make retrofits better, faster, and cheaper, just not yet available in terms of CSA approval or warranties or other issues. But I think that there's going to be quite a push to expand that, both from Canadian companies and from international suppliers. And part of this work has been really looking at a relationship with best practice partners across the world. So we've looked at partners in the UK and Germany and France, and BC Housing in BC is a real leader in Canada and North America, and looking at what best practice could look like. And then when we look at the retrofits, market holistically, just the type of building that we studied here, cross country, that's $62 billion or more in direct construction costs, and we all know that most of that is direct labor, which is a local job. So there's something quite exciting about that. And the main thing is really to say, let's not tear this stock down. There was a time when a lot of public housing companies were tearing this stuff down. Now, thankfully, they're not, just because of the gap in supply. But another real reason to do it is both the economic issues. It's in our experience, it's always been cheaper to do a retrofit than to tear down and rebuild, including the case of Soble Tower, which is quite a it's a pilot project, and there's costs associated with being the first passive house retrofit, but it's still less expensive than tearing down and rebuilding. And people often forget the actual quite high costs associated with tearing down a large building with dealing with asbestos and other things. And what this chart is looking at, and I forgive having a chart with tiny numbers, is really embedded carbon. And so we all know that concrete, old concrete from the 60s, has a high carbon content. And so the issue was with the Soble Tower, this was a little study we did with them, is that if they tore it down and then they built a new passive house building, it would take 180 years until they recouped the energy lost or the carbon lost in tearing down that concrete frame. So it's a real showcase as to why reusing existing concrete frames is critical, but just because of the enormously high carbon content from concrete made in the 60s and 70s. And then this is looking sort of nationwide. If we did a comprehensive retrofit program of just this building type, we could save about 3 megatons annually in mainly natural gas heating costs. That's the conclusion of this case study. So I'm happy to answer any questions, and thanks for the time.
Thank you, Graeme. This is Alan Belanger. I'm the Secretary Treasurer of the chapter. Thanks, Graeme, for a very interesting presentation. It was very, very interesting to see what we can do with the existing towers that are available to us. I do have one question from an attendee. It is, did you encapsulate the existing balconies in the new exterior cladding?
No, actually, that's a great solution, and we've seen some examples elsewhere that have done that, where you actually increase the GFA and turn the balconies into an interior space. In this case, the balconies were simply removed, so we brought it back to the slab edge and encapsulated the slab edge into the new envelope, but the balconies were removed. But that question of what do you do with balconies? In terms of encapsulating, I guess there's really 2 options. One is that you mitigate it in terms of, you could have a glazed layer if you glazed up those balconies to turn it into a interstitial space, kind of like a winter garden, or as the attendee is suggesting, you could just turn it into indoor space, and it's just an increase. What we have found is that if you want to turn it into indoor space, there's actually a tax hit of the owner, because the owner suddenly has more GFA and their tax roll goes up. And there actually might be a site plan issue in that the zoning bylaw may simply only allow for a certain GFA on the site. And those are very boring technical issues that are quite real. But we have found in the city of Toronto that if you were to enclose the balconies as an indoor-outdoor space, so it's not interior GFA, but it's more of a winter garden, that they would waive any zoning issues with that, or tax issues. So that's promising.
And we have one more. It's asking, can passive house designs be applied to the thousands of glass towers we have been building in the GTA in the past 20 years when they reach the end of their lives?
That's a fabulous question. I'm writing that down. So I think what's really interesting about this case study is, or this project, is that we were able to really evaluate what are the initial benefits of buildings of this vintage, and you know, there's many of them. The main one being they've provided hundreds of thousands of units, and for in many cases quite large, you know, family-sized units. And the other benefits that really showed in this project is the high quality of the concrete frame. So very little structural work is often required. But also the robustness of the block wall and brick veneer, that you can adhere to it. You can, you know, if you put in helical ties, it can support weight. That it's a real advantage to have that masonry. And also the relatively small window to wall ratio means that your glazing costs are a lot lower. Both you have lower glazing costs, you have better thermal performance, and also not a lot of thermal gain. So in terms of a passive house model, passive house generally wants a lower window to wall ratio than we're accustomed to these days. And the Soble Tower is about 18% window to wall ratio, and I think typical passive house would be around 25 or so. So enter in the condos. You know, some of them, I will say, some of them are like very well considered, very well designed, curtain wall buildings, etc. But I think what we're all quite worried about are these window wall buildings, of which we're already concerned about, you know, gaskets and sealants and you know, water penetration, you know, 25 years in. So I think what is a challenge about the condos is that without essentially delaminating the window wall and putting on something else, you're not going to change your window to wall ratio. So we may need to look at a different standard. It may be very difficult to meet an interfit with that building type without some radical changes, which is why the older buildings in a way are more amenable to deep energy retrofit. But I think a case study to say what should the standard be and what are reasonable expectations of savings, both from air tightness, heat gain, and just central systems in those older condo buildings, because the you know, the condo boards, they want to do right by their buildings, and I think that retrofits are going to start happening to the first generation of those, you know, late 90s, early 2000s buildings. Those are going to come on queue for work sooner than later. So great question.
All right. Well, thank you very much, Graeme. There are no other questions. I can't see any in the chat section right now. I'd like to thank you once again, Graeme, for a great presentation. And just to remind the attendees that we have one more webinar in our series this afternoon at 2:30. It's the presentation from Stubby's precast that we had to reschedule due to some technical glitches on our behalf. So we hope you will join us then. And once again, Ken, thank you. We look forward to hearing from you again in the future.
Thanks so much for having me, and good luck with the rest of the series.
All right. Thank you. Thank you to everyone.